Okay, so section 2.5 is limits at infinity. So limits at infinity mean we let x go to infinity or get very, very large, or if x goes to negative infinity, that means it's getting very, very, very small and negative. You may have, thought about this concept before, but called it by a different name, end behavior, in your pre-calculus class. I'm not sure. But one of the first things that we might encounter as a limit at infinity is that the limit is a number. And this happens, really when we have a horizontal asymptote. So I wanted to look at the function arctan of x first. So if you recall from trigonometry, arctan of x has a range of minus pi over 2 to pi over 2. I'll just draw that as kind of a dashed line. And it looks like kind of an elongated S shape. And so here there are two horizontal asymptotes, two end behaviors. I'm going to write it in calc terms now. Basically we would say the limit as x goes to infinity of arctan of x is equal to pi over 2. But if we were to take the limit at negative infinity of the same function, it has a different limit, minus pi over 2. So pi over 2 and minus pi over 2 are both called horizontal asymptotes. Okay, so hopefully that's a term you've heard before. Okay, but now we're connecting the idea of the asymptotes with the calculus concept of a limit. Okay, so next I want to talk about infinite limits at infinity. So a quick example of that would just be the cubic function. So if we look at the cubic function, just do a rough sketch of that, it looks something like that, right? So if we were to take the limit as x goes to infinity, so what does x cubed do as x gets very, very, very large and positive? Well, it also gets large and positive. The y values increase without bound, and so we say the limit as x goes to infinity of x cubed is equal to infinity. And then similarly, if we look at the limit as x goes to negative infinity, well, looking at the graph, that would correspond to kind of this piece of the graph. The y values are getting very, very small, and they're decreasing without bound, so we would say the limit here is negative infinity. Okay, so that's the idea of infinite limits at infinity. So just to go back, now we've seen an example of approaching a number as x goes to infinity, and here's an example of approaching infinity as x goes to infinity. Okay, so I want to summarize just in general the end behavior for polynomials, and you probably have seen this before too in the leading term test in your pre-calculus class. Okay, but this going back and revisiting this concept might help you with this section. So if you remember the leading term test, if we're looking at a general polynomial, okay, which I have written here, p of x can be generally expressed as a sub n, x to the n, plus a sub n minus 1, x to the n minus 1, and so on. And we're really interested in what's called the leading term, or the term that involves the highest power of x, and we call n the degree of the polynomial. It's the highest power. So if n is odd, and these a sub n's are considered the leading coefficient, if n is odd and the leading coefficient is positive, we actually are going to have behavior at infinity that's very similar to x cubed that we just examined. So in this scenario, x going to infinity means that f of x is also going to infinity. X going to negative infinity means that f of x is also going to negative infinity. Now, if the leading coefficient a sub n is negative, basically you could take, a general cubic shape, reflect that over the x-axis, and here's your general end behavior. Okay, so remember the leading term test tells you about end behavior. And now we would say as x goes to infinity, f of x goes to negative infinity. And as x goes to negative infinity, f of x goes to positive infinity. Okay. Now if n is even and the leading coefficient is positive, the behavior looks something like a upward facing parabola at the ends. And so here we'd have as x goes to either plus or minus infinity, f of x is going to positive infinity. Whoops, it's not very well expressed there. Write it down here, okay? And if the degree n is even, so the highest power is even, and the leading coefficient is negative, we have end behavior looking like this. So as x approaches plus or minus infinity, f of x is now going to negative infinity. Okay, so that's kind of a recap of the leading term test. This might help you with some of the limits that you're being asked to evaluate. Okay, so next I want to talk about rational functions. So this is another pre-calc concept that we're expanding on in calculus. So now we're looking at a rational function, and hopefully you recall the cases for when a horizontal asymptote occurs. And a horizontal asymptote is a limit at infinity. Okay, it was the first example that I showed you with the arctan. Arctan has two horizontal asymptotes. So a rational function is going to have horizontal asymptotes in two different cases. It's going to have horizontal asymptotes when the degree of the numerator is less than the degree of the denominator. And it's also going to have a horizontal asymptote when the degree of the numerator equals the degree of the denominator. Okay? So if the degree of the numerator is less than the degree of the denominator, so that's that first case here, our horizontal asymptote is 0. And the reason that happens is because the denominator grows so much faster than the numerator, that the entire fraction shrinks to 0, gets closer and closer to 0. If the degree of the numerator equals the degree of the denominator, well then the horizontal asymptote is a sub n over b sub m. It's the ratio of the leading coefficients. And then this isn't the last case here, I'll mark it in green. We don't have a horizontal asymptote here. Here we'd have a slant asymptote. Okay. So with a slant asymptote, that occurs when the degree of the numerator is 1 larger than the degree of the denominator. Okay, so how does this correspond to limits? Well, 0 is the limit. It's the horizontal asymptote, but it is the limit of that rational function as x goes to infinity. The ratio of the leading coefficients is the limit of that rational function. The slant asymptote, and I'd recommend that you go through some examples of slant asymptotes, that is, it's going to be a line, but what happens is your function is approaching infinity or negative infinity along that line. Okay, so that also tells you something about the function. So I'm going to stop this video here, and the next video I do will be a couple examples of how to take limits at infinity.